So, we are going to discuss some more aspects of recrystallization during heat treatment of the cold work samples today. As you know, the recovery is the first stage of this process in which the sample will be heated to the intermediate temperature, and recovery is mainly a process in which defects, mostly the point defects and the line defects, they get properly arranged in the microstructure. So, point defects such as voids or interstitials, they get arranged. Actually, voids will be coalescing each other, or maybe they will be combining with the gain boundaries, and dislocations will arrange in a low energy configuration, that is the polygonization we have discussed in the last two lectures. Now, the subsequent to recovery, the important process which occurs in cold work materials is the recrystallization. Recrystallization means formation of strain free grains in the deformed structure. Now, as I said, the two important the process which happens in recrystallization, one obviously is nucleation and subsequent growth of these grains, but most importantly the migration of the gain boundaries from a region of highly deformed structure to a low deformed structure relatively happens, and this is the factor which contributes to the nucleation of the grains. One has to understand the store energy during cold work is responsible for such a kind of processes. As we have seen, the free energy change which is responsible for such a kind of transformation is basically equal to the minus of the store energy, and store energy is because of these defect structures in the material, and store energy is not usually very large. Actually, this is very small, as you have seen. In case of silver, it is about 0.33 kilojoule per mole. So, as the store energy is small, so therefore nucleation is not going to happen because of thermal processes. Normally during liquid to solid transformations, or even many of the solid to solid transformations, nucleation of the product phase from the parent phase happens because of thermal fluctuations. But here it does not happen that way. The process which governs or which basically dictates the nucleation of these strain free grains is basically the second one, the migration of these grains, migration of the gain boundaries actually to the regions of high dislocation density. This process is basically very important. You know that incoherent nuclei which are created by the formation of these phrase lattice by thermal fluctuation does not happen in this case. So, it is the things which I will show some pictures, maybe I will go a little farther and show you that now. See, this is what is a polygonized structure in a iron silicon steel actually, single crystals, which was deformed and annealed for about 10 minutes at 1000 degrees Celsius temperature. As you see here, a lot of grain small angle boundaries you see here, obviously because polygonized structure means these locations get arranged in a particular fashions like these locations get arranged on top of each other, and this form a low angle tilt or twist boundaries. So, that is what you see here. You see a lot of these small angle boundaries created in the microstructure because of annealing treatment, and subsequent to that recrystallization will happen, because recrystallization is after these low angle boundaries has been created, that means this location has been arranged properly in the microstructure. These small grains, strain free grains, will nucleate either on the boundaries or inside the grains depending on the strain level. And that is what is basically the start of recrystallization. This picture is of nickel annealed at 415 degrees Celsius temperature for 10 minutes after cold work. You can see the boundary which is there, this boundary has moved from heavily worked regions, heavily dislocation regions to a little less dislocation regions, and in this process it creates a strain free regions. You see here this strain free region is created, and this strain free region is then becomes a fresh nuclei, a nucleation for the formation of the grains. That is what actually the most dominating process which governs the recrystallization, that is the movement of these boundaries. So, boundaries do get formed initially by the process of polygonization, and these boundaries which has formed large number of boundaries, they then start moving or basically migrating from heavily deformed regions, relatively high dislocation density regions to the relatively less dislocation density regions. This migration, as I said, is basically because of the this concentration difference of the deformed structures, and in this way it creates certain kind of a strain free regions in the microstructure. And this picture is very nice, it has been taken directly from the book of Jena and Chaturvedi. It clearly shows that how a strain free regions can be created inside a grain simply by migrating a boundary. Okay, so that is one of the reasons you should understand how the nucleation happens, and then once the nucleation of these grains happens, they start growth. That we will discuss even in subsequent lectures, but first let us discuss about that. Now, cold work process also leads to what is known as deformation bands. Okay, that means sharp lattice misorientations inside the grains. That means you have one grain in which some regions will be heavily distorted, what is known as sharp lattice distortion will happen in some part of the grains. That depends on the obviously type of grains, their relative orientations in the samples, and these sharp or heavily deformed regions are basically what is known as bands in the literature, and these bands actually contains more number of defect structures, and therefore this probably was a band in the microstructure. You can see there are bands like this develops, and these bands actually starts moving, okay, inside the grains during subsequent annealing processes because of the availability of the thermal energy up to the system. And then finally the boundary which is demarcating between the two grains are forced to move from heavily deformed region to the small deformed regions. Okay, that is the main reasons for the recrystallization, and I will just go back again to these slides which I was discussing with you. So, this second aspect which is migration, it does not involve a nucleation of the grains, but it leads to nucleation of the fresh grains. So, that is what is shown here. You see that this has large number of dislocations, this is one part of the grain, and this has less number of dislocations, and because of that the gain boundary is moving from this side to this side. Okay. And that creates in this part of the region a strain free part of the grain, and that is what becomes a nucleation. Now, once the nucleation happens, the nucleation rate, which is obviously most important aspects in dictating how many grains we will be forming, as I said, it depends on typically by this formula. So, n dot is the nucleation rate, it depends on the number of grains or number of basically atoms, and nu is the frequency of jump, and this one is the exponential term which is equal to 16 pi gamma q v square by 3 E s square plus delta g I plus k t. As you see here, basically here you have to understand one thing, as compared to the classical nucleation rate equations, G s is basically it's not it's basically converted into E s by V, and other things are not considered here. So, E s is basically strain energy stored, V is the volume, gamma is the interfacial energy which is there, and K is the Boltzmann constant, is the temperature, delta G I is basically coming from the aspects of, as I discussed, is basically coming from, let me see, this is a energy which is derived from the what is that, just a minute, let me check. Yeah, so delta Gi is basically activation energy for the gain boundary diffusion. Yes, that is what we have been discussing. This is the activation energy for the gain boundary diffusion. So, gain boundaries which are moving because of these difference of the dislocations on the both sides of the gain boundaries, or that is what comes into picture. So, as you see here, this is a negative term, this is a positive term. So, if you want to have a higher amount of nucleation density, so you need to have a a large value of the gain boundary migration. Why? Because this negative part will be reduced further as you go along. Remember that ES is independent of temperature. ES is the stored energy, stored. It depends on the cold work, basically depends on the strain rate, depends on the cold work, depends on the type of material, it depends on even type of deformation processes you are adopting, but it doesn't depend much on the temperature. So therefore that means NT, N dot is basically a strong function of the temperature. It depends, it's just like nucleation rate in case of classical solidification. If you plot nucleation rate versus undercooling, after some point in time it shoots up, it increases rapidly, and that's exactly same thing happens here, because it's exponential minus 1 by T terms. Therefore at a certain value of the value of the temperature, it will increase rapidly. Although we cannot talk about exactly undercooling here because this is solid state deformed structure, but we can always make this plot as a function of temperature, and if you do that it will have a similar kind of things, it will rapidly increase. So therefore there will be burst of nucleation happens in this case also, recrystallization also, and this is mostly dominated by these migration of the boundaries. That is one important aspect which must be remembered always. So once the new grains forms, subsequent process is nothing but growth. The kinetics by which this whole thing depends on is known as the Johnson-Mel-Abrahami type of equation. As I told you, Johnson-Mel-Abrahami, these three scientists, they develop a model, and this model dictates you how the grain actually grow. So we will discuss in subsequent part of the lecture what is this equation is. As I tell, the equation tells you the rate of the growth of basically rate of the process, basically both nucleation and growth, is given by 1 minus exponential minus kt to the power n, and where n is nothing but n is equal to 4, normally it is basically exponent, growth exponent, and k is a constant, and k is basically given by pi n dot g dot 1/3 and is pi by 3, where n dot is the nucleation rate and g dot is the growth rate. So now question is that we must know how this equation is basically obtained. This equation has many interesting aspects because this equation integrates nucleation and growth together. So as you know, here k is the most important factor and the n is the important factor. It depends on the time. It's a kinetics, therefore it must be dependent on time. So it's basically 1 minus exponential minus kt to the power n, and n is the time exponent, which is equal to normally 4. It can be equal to 3 also depending on the process, but here normally recrystallization is taken as a 4, and k is a constant. It's not exactly a constant, it also depends on the temperature. It is basically equal to pi by 3 n dot g dot to the power 1/3, where n dot is the nucleation rate and g dot is the growth rate. So how do we get this equation? Well, this equation is obtained in a very nice manner, which I will do that in the board until let me just do it so that you can understand. Now question is this, as I said, let us consider a transformation, simple transformation, alpha going to beta. Okay, it's same as like recrystallization. The deformed grains transform to strain-free grains, and as you know, rate of this process depends on, obviously is a function of nucleation rate as well as the growth rate, right? Both. As I said, the growth of these strain-free grains is basically dictated by the gain boundaries energy. At small grains you will have a larger gain boundary area, so you have to reduce that, grains actually start coalescing and grow. So finally rate of the whole process depends on basically nucleation rate and the growth rates. So let us consider a very short time scale experiments in the time region of 0 to tau. Tau is basically very small time scale, and now as you know, as you increase the time from tau to tau plus d tau, the nucleation, the total number of nuclei basically will be equal to nucleation rate multiplied by volume multiplied by the time increase, obviously. Okay, so this is the time increase from tau to tau plus d tau, and d tau is actually very small increase of time. Because of time increase, total number of nuclei will be equal to nucleation rate multiplied by time multiplied by the volume, because nucleation is per unit volume normally, and this is the total number of nuclei which will form at the time when you provide sufficient driving force for the nucleation. So now let us assume that this growth is also will happen subsequently. Normally the major important thing which we discuss is that suppose if we consider a big grain and these are the nuclei which is formed. As the nuclei grows, they will impinge on each other, then they will stop growing. That is what happens. All the nuclei will start growing around it, and when they impinge on each other, these spheres, then they stop growing. That is what is the end process. So normally the nucleation and growth will happen together in these cases. They will not be happening one after another, because nucleation is the start process. Once it starts, then there is enough driving force is available for each to grow for the recrystallization process also. So now question is that if I have a growth rate given by J d dot, okay, of these grains, and if I want to calculate what is the volume change, suppose this is the volume which beta phase is forming, suppose this is the volume change. So that's obviously will be equal to 4/3 pi r cube, because that's the volume of the sphere, and obviously growth rate is gq, that's why, multiplied by the time suppose which you have spent after tau. Obviously tau was the time in which the things have started, so tau plus t will be the time which will be specifically spent on the growth, although this will happen together. So it does not matter whether if you use this equation like this or tau cube, does not matter, it will be similar, because tau is a very small time scale. So that means this is the sphere which is with the change of volume, and which will happen, okay, multiplied by v dot this one, okay. So we should write it v n dot d tau. This is the nucleation rate, nucleation total number of nuclei, then the growth, okay. So it assumes that all of these guys, all of these things going like a sphere, which is not always true. In fact, if you have seen the gain boundaries, they are not always looking like a spherical. So that's the major assumptions which is made here. Second assumption is made that is basically we always assume that these nuclei are growing only in the untransformed regions. So you have suppose the grain which is not yet fully transformed, and there is a grain which is already been transformed. So likelihood chance that the nuclei which will be sitting here, they will be growing much faster than a nuclei which is sitting there, because you already lot of strain energy has been reduced because of the formation of these nuclei. So therefore chances of growing these nuclei is much higher than these ones, and that's why one of the assumptions on this model is that the untransformed regions has more propensity to form for the nuclei to grow than the regions which are already transformed and some part is remain to be transformed. So in such a situations, this equation tells you that the volume which is being the change of the transformed volume because of the transformation is basically is nothing but the apparent volume is not exactly the volume which has got completely transformed, okay, because unless and until all these whole spaces are actually getting transformed, you cannot really talk about what is the actual volume of transform. So now if I integrate that, okay, if I integrate that, what I will get? Simply I get transform B, that's equal to nothing but dv beta E, okay, dt, right, or d tau rather, sorry, let us put tau, otherwise it will be mathematically not sound. So now if you do that, and that's you can do it from 0 to t time scale. So what you will get? You will get v beta E is equal to, and this is q, so 1/3 it will become pi, that's what you have seen, and that's equal to v n dot g dot 1/3, okay, g dot 1/3, g dot q, sorry, g dot q, and t to the power 4, okay, and this is exactly I wrote. So therefore in the expression which you have seen, now how will I do that? Normally this is the total transform regions, and we have to consider fraction transform. Okay, y was 1 minus exponential minus k t to the power n, right? That's y is a fraction transform, and this is the total volume of V created. So fraction transform, we can always write down dV BE by V B E, okay, oh sorry, dV B is the transform, okay, this is divided by V is equal to, always write down basically equal to, what is better, write down like this. So that means if this is the apparent volume and this is the volume which is actually transformed, this must be equal to V divided by V minus Vb. Remember, this V is basically the volume which is present in the material, this whole volume of the grain, and V beta is what is being transformed. So the remaining volume V minus Vb is what is untransformed. So this region, as I said you, as more propulsively transformed, has to be accommodated somewhere. So therefore the apparent volume divided by the actual volume transformed will be equal to the volume which is totally occupied divided by the volume which is left over. That's understandable. Volume which is been left over will be more propulsive to transform. Okay, so that's why if you increase this this one V minus Vb more, that means when Vb is very small, then this ratio will be equal to 1. Then the whole area is equal propulsively to transform. But as the Vb is increasing, so that means, sorry, Vbe is increasing. As the Vbe is increasing, the chances of transforming these regions is lower than the regions which has got untransformed. Okay, so now if you do the mass properly, that means this one if you do properly, so that's nothing but, I can write down from that, Vbe is minus Vbe is equal to dVb by V, and that tells you log of 1 minus y, and where y is basically defined as Vb by B. B is the original volume and Vb is the transform volume, that's the fraction. So that's equal to 1 minus exponential minus ktn, and it's easy to understand that if I put this one, so this become exponential minus pi by 3 v n dot g dot q t to the power 4, and this is 1 minus y, log has gone there. So because we are integrating these things, so y becomes this, y will be this, and this particular expression which is derived basically is nothing but from this equation is known as Johnson Mel Abraham equation. Okay. Okay. I'll write it here because we cannot see it properly. So y is minus 1 minus exponential minus pi by 3 v n dot g dot to the q to the power 4. Remember, this is a fraction, okay, because it's exponential minus term, and n dot is always very small number, it's 10 to the power minus 30, minus 40, and g dot is also very small number. G dot actually, so therefore depending on the type of process you can modify this expression. Nucleation rate can be easily obtained from heterogeneous or homogeneous type, but Goro rate will depend upon what kind of process going on. So we see in our recrystallization gain growth, the G will be depending on something else. Okay, G is not same for all the processes. So in a paralytic growth, diffusion control growth, G has a different kind of expression than in martensitic growth or in case of recrystallization gain growth. So depending on the type of process, these factors G and n dot will change, G dot and n dot. And remember, these exponents on the time, it can change also, because some processes actually time is it's a very strong function of time. It can be order 4 or 5, and some processes will be the exponent will be order 2 or 3. but this is the classical expression. So, many cases people write it in this way also, 1 minus exponents minus k t to the power n, that is generalized expression, and this is what is generalized Johnson Mel Abrami expression. What does it provide us? It provides us very important things. Once we know k and n, we know the whole things, what is happening. We know what kind of time dependent exponents it has. We know also the kind of nucleation and growth process going on in the particular phase transformation. So this is a very important expression things. The way I derive is basically looking at diffusional transformations from alpha to beta, but it can be derived using other kind of transformation also. In the book it has been done this way, that's what I have done so that you can understand very clearly. So what I will do is next lecture, after now that I have discussed with you how the recrystallization happens and what is the kinetics on which it depends on, our next targets will be to discuss how these grains actually grow, the stain-free grains which forms inside these deformed crystals, how they actually grow. So this we will be discussing in next lecture, the growth of these grains, and subsequently we will talk about a little bit about how we can actually use this equation to explain both all the whole transformation process, and we can show how plots can be made from different deformed materials to obtain the interesting parameters of such kind of kinetics.